Good morning, everyone. I am Federica Filippini, now postdoc researcher at the University of Milano Bicocca, and in this presentation I will give some insights of my PhD work concerning the resource allocation and scheduling of artificial intelligence applications in the computing continuum. Why is this a relevant problem? It's apparent that the market interest on AI has been growing faster and faster in the last years. However, everybody working on AI and deep learning knows that most of the time, the hardest part in developing an application is not AI itself. There's a huge work concerning data collection and pre-processing, monitoring, post-processing, but also, and here's where my work comes up, the designing and development of an infrastructure that supports the execution of the training and inference process. Indeed, the resource landscape we face is more and more complex and heterogeneous. We have a computing continuum that starts from IoT and other small devices that of course are used to collect data, but also to perform an initial processing, particularly for latency-sensitive applications. There are edge servers that have a slightly larger computational capacity and still guarantee very good performance in terms of latency and privacy. And finally, we have the cloud that makes accessible ideally unlimited resources according to pay-to-go models and at the price of larger overheads for data communications. These two boosts together entail that developing efficient resource selection and placement algorithms is crucial to orchestrate and exploit at best the computing continuum resources. I tackled this problem both at design time and at runtime, where the initial production deployment needs to be periodically reevaluated and adapted to new environment conditions. Let's consider a use case application that comes from the AI Sprint European project I worked in. It is a 7 components application that processes images collected by drones to identify and classify damages in wind turbine blades. The 7 components have various characteristics in terms of computational requirements and can be executed on different devices in the computing continuum. For example, the first 2 components that perform initial checks on the images are lightweight and can be performed directly on the drones or offloaded to local edge devices as the operator's PC. The intermediate component perform blade part identification and general object detection tasks and can be performed either in the edge or offloaded to the cloud. And finally, the last component that perform the most complex tasks need the power of cloud resources. In general, we can also consider that AI application components are themselves deep neural networks that can be partitioned to facilitate the offloading. So an optimization framework needs to select not only the best resource at each computational layer and map the components to the selected devices, but also identify the best neural network deployment. At design time, we tackled this by developing Space4ID, which is a tool to determine the minimum cost placement, considering a maximum value of expected workload, and satisfying user-imposed constraints on the response times of single components or multi-component pipelines. We developed a mixed integer linear programming formulation that minimizes the cost, the amortized cost of edge resources, and the usage cost of cloud resources and functions as service resources. This is coupled with several heuristic algorithms ranging from random greedy to tabu search, for instance, that achieve very good results with respect to the state of the art with minimal deviations between the real and the predicted costs and execution times when validated in a system prototype. However, as we said, determining a good quality solution at design time, unfortunately, is not enough. Indeed, this provides low costs and performance guarantees considering an expected workload value, but this value is usually not fixed at runtime. Instead, the fluctuations in the workload easily determine overspending if the resources remain idle because the actual workload is lower than expected, or instead the violation of the response time constraints. Therefore, the deployment needs to be adapted at runtime, performing, for instance, scaling or migration actions to deal with the varying environment conditions. We developed Space4IR, which is a heuristic-based solution that is the runtime counterpart of Space4ID. It treats a similar problem considering not the amortized cost of edge devices, but instead the energy cost of their running resources. And it is designed to run in a tiny fraction of the execution time of Space4ID because adaptation decisions need to be taken almost in real time. This again achieves very good results when validated in a prototype system, but unfortunately, again, heuristic solutions have some limitations. Indeed, they are based on model assumptions that usually do not hold in real system, and in particular, designing a model may be even infeasible due to the complexity of the problem. We resort to reinforcement learning, which is becoming popular because it automatically adapts, it learns how to adapt to fluctuating environment conditions. However, it is characterized by a long training time, and it takes initially bad decisions that can have a strong negative impact on the system. So we designed Figaro, which is an integrated framework that leverages the knowledge of Space4ID and R to perform an initial offline pre-training. This allows to finally follow very well the pattern of the workload and achieving significantly better results than an agent that starts from a random policy. So we discussed about the design time and the runtime management of AI inference applications. The last part of my work concerned the management of deep learning training applications executed in GPU-accelerated private or public clusters. Here again, we want to minimize the execution or energy costs plus penalties due to the violation of deadlines. And we did so both from the point of view of cloud end users and from the point of view of the providers. In the first case, based on the queue of submitted jobs and based on a virtual machine catalog and on the expected execution times of the jobs on the available resources, the optimizer determines which resources to assign to the job and how to place them on the cluster nodes. This problem is solved periodically, and every time a job is submitted or terminates the execution, and jobs can be preempted and resumed in a next scheduling point if the resources do not allow to run all of them concurrently. Moving from the perspective of the user to the perspective of the provider, we have to change the description of the cluster because, of course, we don't have virtual machines, but physical nodes with fixed configuration. And we enabled GPU sharing to allow a low-demanding job to share resources, improving the overall utilization. Finally, we consider stochastic execution profiles because jobs do not necessarily run up to a fixed number of epochs, but instead may terminate with a given probability based on, for instance, the accuracy level. So we developed a mathematical formulation to minimize the cost, considering penalties for idle resources in the case of the user's perspective and considering the expected costs to deal with the stochasticity when we are in the other scenario. And we developed a heuristic algorithm that preprocesses jobs, sorting them to assign resources first to the ones closest to the deadline, to assign them to the proper nodes, and finally trying to minimize the GPUs that remain idle. This also achieves good performance with a negligible deviation between the real and predicted costs in a real system. So to conclude, we discussed the design time management of AI inference applications, developing a tool that achieves up to 60% cost reductions with respect to the state of the art, with a small gap between real and predicted cost. This may be enhanced by exploiting Bayesian optimization to reduce the initial processing that we need to consider cloud resources. For what concerns the runtime management of inference applications, we achieve again good results with respect to the state of the art, improve the positive impact of an initial profile offline in training for reinforcement learning agents that should be validated in a prototype environment and may benefit from considering federated or multi-agent or hierarchical reinforcement learning to deal with complex pipelines of multiple components. And finally, for the runtime management of training applications, we proved the positive impact of GPU sharing and now consider to support scenarios where larger applications are distributed among multiple cluster nodes. That concludes the presentation, and thank you.